So I'll be covering failure modes in structures. Failure modes in structures are quite important. Here you can see the failure of our aircraft where it failed at the wing location. That's a fuselage test of a 777 that split due to pressure being applied, and the wings bent upwards, and the interior at the maximum pressure caused a failure at ultimate loads. This is a very expensive test, and to avoid expensive tests, it's important to do analysis to prevent those situations from happening in the future. What's the role of analysis to me? You're going to test it eventually anyway, but the role of analysis is to prevent, you want to be able to save money, right? So like, what if I spend millions of dollars to manufacture this aircraft, and when I go and test it, the thing fails? Like, I wasted my money. That's why you analyze things in advance. And not only that, if you don't have any test validation, it's good to carry some amount of uncertainty factor, because you're not perfect and I'm not perfect. So you're going to carry some of that. Another point I want to point here is that there are a lot of different failure modes, and they're very complex in nature. Structural systems have a lot of different failure modes. What are structural failures that occur? Like, where do they occur? Sometimes the hardware is not properly qualified. For example, you didn't test it adequately. Another situation is that you thought that the flight loads during flight were the right ones, but in fact, it was the wrong ones. It could be higher. An example of that will be the American Airlines 587 that crashed in Queens, New York. The rudder load that was applied was higher than what it was qualified. The input that was put in was higher. So that situation is one that could happen as well, where you are outside of the bounds of what you qualified, because we didn't expect it to be higher, maybe, or nobody ever thought could be higher. Hardware defects could be caused, like in this example, there's a defect in the manufacturing, and that's a stress concentration that can cause a failure. Hardware damage, we have an impact damage event on a composite that nobody saw, that on the compression load causes failure. What is the biggest lesson learned in the aerospace industry in particular, but also mechanical, like the Toyota incidents with the brakes not working, those cars not working, the brakes was not working for those cars? The lesson learned is that sometimes a lot of these failures do repeat over time, and they repeat because we don't remember the lesson. The lesson gets repeated over and over. That lesson learned gets repeated, but nobody remembers the lesson. So they keep making the mistakes over and over and over. So it's important to really understand, as a designer, understand what the failures have been in the past, so those don't get repeated. Carelessness, unit inconsistencies have led to, like, mission to Mars, failed due to unit's consistency. For example, there was an adhesive in the floor that looked the same color, but they ran out from one of them. So the technician thought, oh, I can use this other one. Why not? And they used it, and it caused a failure. Well, they didn't know, right? It was a difference in one number in the spec. And so the person thought they could use cutting corners, you have the schedules they have to meet. You're cutting corners to get it right, supposedly, but you're cutting corners, you don't have all the facts right. There's a lot of examples here. The bottom one is the units issue with the $125 million loss due to a miscalculation of English units versus metric units that failed. Structural failures have also been caused by dishonesty, in purposely hiding a technical rigor. For example, switching a material for a cheaper one and not telling somebody that that's what was done. That has happened both in aircraft applications and rocket applications. So that's why, in my personal view, honesty starts. I mean, if it hasn't started now, if it didn't start when you're growing up, perhaps you should really work hard to rectify that. And honesty here means, integrity, technical integrity, ensuring that, you're applying those concepts here in school, right? When I was a student, and I'm recording myself when I'm saying this. When I was a student, I was tempted to cheat sometimes. If somebody told me, oh, I have the answer to that one. But the reality is that if you do that, what you're doing is being dishonest to yourself. So sometimes it's better to get a worse grade. And I did. I got sick, and my family got sick during the finals in my bachelor's degree. And you know what? I sucked it up. I took the C. But what you know what happened though? That made me stronger as a human. Why? Because that C sucked. And now I have to figure out a different way of getting maybe, I mean, my GPA, overall GPA was great. So, but I had 3 C's in my undergrad that were not what I wanted, but they were outside of my control. But I could have cheated and got an A, right? So honesty goes a long ways, and I think having those hurdles, those hard issues in life are useful. They make you stronger later in life. So when you're there now in industry and your manager says, where is it at? Where is the product? And then you're here making numbers up in PowerPoint to look good. What you're doing, you're putting lives at stake. And the reality is that dishonest behavior has to be fixed now. It's better to get a bad grade than trying to fake one, because it's going to catch up to you eventually. It's going to. I've seen it. Okay. Inaccurate characterization of material properties, not measuring properties properly. We see that with composites. People looking at failure mode. For example, they looked at fracture, fatigue, strength, buckling. Oops, I forgot about galvanic corrosion, which is a metal that gets corroded because the metal is next to a composite, and that causes galvanic corrosion in the presence of moisture. And everybody forgets that, for example. So when you're designing a system, not only have to understand the environments you're going to operate in, you got to also understand what are all the different failure modes you could see. And that's why you have to then consult with other engineers and not stay in your cubicle thinking that you know it all, because it's not going to work that way. Oh, no. This is the hardest one. Sometimes there's failures and we don't know why. And we're trying to figure out why. There are times that you do everything you can and you were honest and you tried everything, but after you tried everything, it didn't matter. There's still a failure. But that's why you test, right? That's why you test, because you don't know everything. And the test is going to tell you if you got something wrong. But I don't want to have that failure, sure. But failure is acceptable in those scenarios. Failure is an option. It's okay. It's going to set you back a couple of years. And you want to do everything you can to prevent it. You're going to have aircraft crashing. You're going to have rockets exploding. Humans may die in those situations. But the important thing is that lesson that you learned from those situations is applied in future designs. Is that clear? Manufacturing errors like improper heating, the incorrect surface finish being applied, especially with additive manufacturing now, where you have surface finishes that look fairly rough. Assembly errors where they put the wrong torque, the incorrect sequence, and things like that. Unapproved parts, I already covered that. Here's an example of an unapproved part where a satellite was carrying, a satellite was being carried, and they found that there's the wrong part being used in this system. And an investigation found that there's falsified records showing that there's an issue with a particular material being used. So what are the systems that we want to look at? The statement here, really the statement is to design systems that can survive the launch environments that are quite complex. And here I'm showing a rocket, but it could also be a wrench. It could be a car. It could be whatever you want it to be. At the end of the day, you have defects in this hardware. You have variations in the manufacturing. Not everything. When you manufacture something, it's not going to come out the way you put it in a drawing. It's just not going to be. It's going to be off. And if it's off, somebody's going to ask you, is that okay? That's where analysis comes into play. Testing may be even necessary. If the analysis confidence you have is low, you better test that. If you design the fuselage to be thick about 0.12 inch, but then you manufacture it and come out to be 0.09998, that's a problem. I need to analyze that. but you want to use analysis techniques that are validated. Important lessons to keep in mind is dangerous to assume that structures are defect-free. Critical parts and potential faults should be identified early in the process. You want to identify all the environments well. Like if you're going to see a part that's going to experience temperatures and environments, it's going to experience loads. You want to get those loads right, right? So if I'm going to design a diving board for a swimming pool, I want to calculate what is the maximum weight I could experience for that diving board as a designer, and making sure that I design a good diving board that counts for 99.99% of the population. You want to do that study correctly. You do the same thing with an aircraft. You determine what is the envelope of the design and what I need to consider in my design. Materials and processes should be adequately characterized, and a lot of times we forget that there's interactions between the structural discipline and other disciplines. For example, it's possible that the deflections of the disc spinning is too much and it can start interfering with other areas of expertise, like a clearance that you need for sure. There are situations where you have a thermal environment that's confounded by these structural loads or structural behaviors. Yeah, so that's one of them. Failure modes include brittle failure, ductile failure, overload. Then you have plasticity, elasticity, or elastic behavior, dimensional instability, and the general wear stuff like fatigue, cracking, creep, relaxation, and fretting. These are things that we'll be covering a little bit later on in this course. Environments that can be painful, I've seen so many failures due to these environments. Stress corrosion cracking, high temperature corrosion, hydrogen embrittlement, hydrogen assisted cracking, oxidation. These are things that I've seen over and over cause failures in multiple systems. Thermally driven problems where you have a CTE mismatch, like the metal I discussed, connected to a composite, where the difference in expansion of the two materials causes the bond line to be stressed and it comes apart. Thermal shock, melting, erosion, and buckling and crippling are other failure modes that need to be considered. I do have a question. No, you can see hydrogen failures in ground systems very, very often. Not very often if it's not accounted for correctly. Then you have the failure modes that are more global, like the materials type, metals, laminated composites, sandwich structures, joints like bonded joints. And here what I show you is a catalog of failures in aircraft. Corrosion was many of them. This percentage of failures. Fatigue, is one of the highest one. Brittle fracture, 16%. Stress corrosion cracking, about 6%. The source here is given here at the bottom. It's called Why Aircraft Fail. I invite you to read that. It's a special publication, but it's very helpful to see. Like if you're going to design something, this is a very nice publication to look at. Failure modes for an engine. I love this plot. This table is great. What it shows is all the components of an engine in the y-axis. In the x-axis, it shows all the different failure modes that could exist and maps it to each of the components of an engine. What a great plot. It shows at the top the components, so blades, vanes, discs, spacers, shafts, blades, nozzles, and so forth, and then cases, mounts, nozzles, combustors, and frames. In the x-axis, the failure modes is HTF, which stands for high cycle fatigue, LCF, which stands for low cycle fatigue. We'll be covering those two, don't worry. Creep, erosion, fretting, and thermal material fatigue. Oxidation, so TMF is thermal mechanical fatigue, oxidation, overload, buckling, over temperature, wear, and corrosion. Really good. One of the best tables I've seen. Really like it. Material overload is an issue. I covered some of that. Fatigue failure, we're going to cover that later. Low cycle fatigue, typically low cycles to failure, 10,000 or less. High cycle fatigue, you're looking at millions of cycles. Here's an example of fatigue failure where the Comet aircraft had a situation where the corners of that fuselage cracked and then propagated. You may have heard of the recent 3 or 4 incidents with Southwest Airlines, where parts of the fuselage came off. In Yuma, Arizona, for example, a person passed away because a blade came apart and it hit the window and it sucked the passenger out. So Southwest had some incidents, right? But what did that do, right? There's some lessons there learned there, and one of the lessons you learn after you examine those conditions is there's a reason why it happened to Southwest Airlines and not others. It doesn't mean that it's because they're a cheap carrier. They're a great carrier. I actually fly a lot with them, really good carrier. But why it happened with them and not others is because of their business model, right? They have a lot of short flights, a lot of takeoffs and landing, and they fly the same aircraft many times a day, right? It's a very different business model than me flying to Florida, long flights with United or Delta, whatever. Although other business models are using the shorter flights concept. But if you think about it, what happened there? Well, what happened there is that the aircraft has to take off and has to land many more times a day. What does that mean? Well, on the ground, the delta pressure across the fuselage is zero. But when you go to 40,000 feet altitude, you have to pressurize the cabin. Otherwise, the people inside are not going to be very comfortable, right? And the outside pressure has dropped because the altitude is lower. So that causes a delta pressure across the fuselage of about 9 to 10 psi, and that's stressing the fuselage, right? So now I land again. So I went from 0 psi to 10 psi, and then I dropped to 0. I repeat that 6 times, and I fly that same aircraft like every day, say, right? So I'm putting a lot of stress, fatigue, life reduction into that aircraft. The life is getting dented over and over. So what they looked at was, well, we missed it because we've been looking for hours to failure. We never looked at takeoff and landing, right? So that's why it was missed there. We'll cover damage tolerance approaches, which means there's an initial crack, and that crack that's not something that you find could propagate to failure. So that's an issue there that should be considered as well. And we'll cover some concepts on fracture later in this course. We'll cover fracture as well, and how you prevent aircraft from having a flaw from propagating to failure. Well, you do interval inspections. So here's a crack, initial crack there. You can see here I have an initial crack that start with, and it starts propagating, and then I have inspection procedures that catch it. I have two options. I can repair the crack or let it go. It continues to grow, but I want to make sure it stays below critical, right? I don't want it to go and propagate quickly. Here, the y-axis is damage, x-axis is number of hours of flight. That's the Southwest Airlines example I gave, the picture of it, if you have not seen it. That's another one. 136 aircraft were inspected, and 4 of these airplanes were found to have cracks just like this one. So it's lucky that these other ones did not see it, the extreme failures that were seen. And these airplanes had accumulated a lot of cycles, right? We're not talking about hours necessarily, but cycles, right? Which is different. Creep is another failure mode where it's permanent deformation that occurs as a result of prolonged application of stress. I was a participant of the radio telescope investigation in Puerto Rico. I grew up in Puerto Rico, by the way. The radio telescope there collapsed in Arecibo. And I worked the investigation with NASA. You can find the report in Google. And the collapse was caused at the end was found to be due to creep, because you have a sustained loading condition on the cables that kept pulling the joints apart until there's a point in time that the joints just came flying apart. There's a video in YouTube that shows what occurred there, and that you can read the report to understand what creep is about. Creep can also occur in aircraft applications. There's a situation where a Boeing company's aircraft experienced significant creep within the engine, causing quite a bit of damage to that section. Here's other examples of creep. This is a creep failure of an aircraft titanium bolt. It came apart as well. And then there's another creep example of another airplane that had a situation with creep in the low pressure turbine blade. More examples, a fighter plane had an issue as well with the second stage turbine blades, and a metallurgic investigation found that creep was a major contributor. Other failure modes, melting. If you go too hot, it can be a problem. You can see that a lot with rocket engines. Thermal shock is another problem. United Airlines 585 had several rudder incidents. There's 3 flights that experienced failures: United Flight 585, US Air Flight 427, and East Wind Flight 517 were really caused by potential thermal shock, where it caused some rudder reversal issues. Corrosion can be also a different problem that needs to be considered. Chemical degradation of metals. Here's an example of an Airbus A320 where there was significant failure due to corrosion in the components of the aircraft. Where this is another example of an Alaska Airlines Flight 261 where all the passengers unfortunately perished. In this case, that particular stabilizer jack screw failed due to wear. And so that's another one that people miss, where if you have constant loading, it can wear the part through contact. So a lot of different material failures. I'll pause there for a second so you can kind of absorb it. I covered all of them pretty much, but most of them, not every single one of them. But it's a good map of all the different failures you're gonna have. I will try to go off memory, but you have strength, you have fatigue, low cycle, high cycle fatigue. Then you have the environmentally induced failures like hydrogen embrittlement, hydrogen-assisted cracking, corrosion, galvanic corrosion, buckling. Then you have other failure modes associated with the flaw that can propagate the failure, wear, and then you have erosion. I think I covered most of them, oxidation and things like that. System level failure modes, I'll go for 3 more minutes here, but you have buckling. Here you see an aircraft that had buckles where the fuselage loses structural strength due to compressed loads. And then there's more examples. I have pictures of Delta Airlines and United Airlines with similar situations. You may not see a lot of those things in the news because nobody passes away, then it doesn't become news. But a lot of these situations do happen. Do I fly? I love flying. I'm not gonna stop flying. Bonded joints, when you bond 2 things together, you can fail inadherent, you can fail within adherent, you can fail between the adherents. This is called cohesive fracture because it's failing within the adhesive. Then you can have the situation where it fails between the metal and the adhesive, for example. That's called interfacial failure. And usually that happens when you have poor preparation techniques. You probably experienced it yourself, where you don't clean the surface well and you try to bond something and it comes apart. Maybe at home you try it at home. The same thing happens in industry, guys. The same thing you experience at home with screws failing and bonded joints, bonded connections coming apart. The same thing happens in industry. This is a desired failure mode. I want the joint to be stronger than the metal because this is more predictable than the joint itself. So that's a good thing to have. A failure mode where it fails outside of that joint. That's a preferred failure mode. Bolted joints have a lot of different failure modes. Net section, shear out, bearing, cleavage, tearing apart, pull through. And all these failure modes require an analysis to make sure you're not having a problem with the design. Distortions, you may think distortions are not possible to cause a failure, but if I launch a mission and my optics are all screwed and I didn't count for the distortion of the lens due to the heating environments of my spacecraft, then I have a bad lens that's not able to do what's tried to do, right? So you have to ensure that your models account for the structural deformations and due to the thermal environments that's going to see in space, and that the optics and the prescription that's applied to the optics is able to be effective so that it can do its mission, whatever that mission could be. Could be looking at stars or whatever it is. So the optical performance is important. CTE distortion. I already covered coefficient thermal expansion distortion. Composite failure modes, really quick. There's a composite here. sandwich structure and laminated composites. Very quick here. Failure modes include fiber breakage. You get matrix cracks and delamination, plies coming apart. And then here, I'm going to show you failure modes for composite sandwich structures. If you remind me, I'll bring one, but you have the core failing, cracking here. You have the face sheet coming apart from the core, and then you have shear crimpling. Here's an example of the fiber breaking within the sandwich structure. So those are just some examples. Then you have bearing damage, and both you have bypass load and you have bearing damage that can occur at the hole. And there's ways to analyze these things in real life. And that's called the bypass strength and bearing strength curve. And those curves can be used in the design process. 587, that's accident composite lug failure I had discussed. The vertical stabilizer came apart. And then here's the lugs that failed here, this joint. And the most probable cause was the results of loads beyond the ultimate design. That's what the NTSB report says. And then this is a very good paper to read. It covers a 587 accident, and one of my mentors, Raju, he wrote the paper here with the team. Here you can see aircraft rudders broken apart, and the reason that has happened actually quite a bit, more than 20, 30 times, is because the pressure inside the honeycomb increases when you go to higher altitudes, and that causes the face sheet to blow apart if there's a defect between the face sheet and the core. Impact damage, lightning damage is a problem, hail damage. So here's the kinds of damage you can have in the composite due to impact. I'm almost done. Here's examples of lightning damage and hail damage. And this one is a truck that came at relatively low speeds, but it's such a big truck that hit the aircraft. When the aircraft took off, the pilots could hear rattling. And what they found was that the stiffeners inside were debonded from the fuselage. More hail damage and the windshield broken apart. And the question becomes then, so this presentation is not meant to be like, don't ever fly again. Rather, the presentation was meant to show you all the different failure modes that an engineer that works in this area of expertise should be aware of. So when you design something, it can be effective at surviving this condition. For example, this hail damage was survived because what they do, they have the radome, the satellite system in the front, or the radar system in the front, but they have a cone in the front that is quite damage tolerant. So if you punch into that sandwich structure, it doesn't reach the radar system, for example. So there's ways that people have thought of how to go about this. The windshields, they're designed so they don't shatter to the point that the pilots could be hurt to the point that they cannot operate the aircraft. So a lot of things have been put in place to kind of learn, and I hope you found this presentation motivating for this course. You know, I'm just giving you some feel for what you see in real life industry. With that said, thank you very much.